All right, so we have three equations, and we're trying to get an equation from those three using Hess's law. Okay, so first thing I'm going to do is I'm going to inspect my goal equation up here. This is my goal. All right, and I'm going to make sure that they're in our given equations, which is equations 1, 2, and 3. I want to make sure that they're in there. And so I look up here and I see two carbons, and I look down here, and where do I see carbons? I see that there's a carbon in equation number 2. I see the hydrogen gas, and I look down here and I don't see it in the first equation. I don't see it in the second equation, but I do see hydrogen in the third equation. That's good. And then I see C2H2, and I see it just in the top equation. Now, also, I got to look down here at the three equations, and if I see more than one, then we don't want to mess with those. And so I see O2, I see in equations 1, 2, and 3. So if O2 was in the goal equation, I would definitely want to skip over those because we'd have three choices, and we don't want to have to make choices. So O2 appears in all three equations. And water, H2, appears in two of the equations. So if we had them in our goal equation, we would want to skip over those as well. Okay, all right, so let's work left to right. So I see carbon, two C's in our goal, and I see carbon, and I look in equation number 1, I don't see it. Equation number 2, I see C as in carbon, and I don't see in equation 3. Now, I see that there are two carbons in our goal, and there's only one carbon in equation number 2. So I need to multiply the whole equation by 2. No, equation number 2. So I'm going to copy down equation 2, and I'm going to multiply times 2 everything. Now, since it's already on the left-hand side, I'm going to leave it on the left-hand side. So I say 2 carbons plus 2 oxygen gases gives me 2 CO2s. Put a 2 there. There we go. And since I've multiplied everything by 2, I better multiply the delta H by 2 as well. And since I didn't change direction, it's going to stay minus. So I go minus, what is that? 780. What is that? 367.0 kilojoules. Okay, and I just did that in my head, so let's make sure that's right, and it is. Okay, so I've used equation number 2, so I'm going to use it. We'll just go ahead and mark off equation number 2 as having been used. Alrighty, and I have the carbon. There it is. Now I'm moving left to right. I see the H2. H2 appears only in one place, and that's equation number 3. I'm looking at H2 right now, and I see that it's an equation number 3. And I see in equation number 3, it says H2 plus half an O2 gives me an H2O. And it looks like I don't have to do anything to it because there's only the one H2, and there's only one H2 up there. So I'm going to just copy it down as is equation number 3. Equation number 3, and this one I did times 2 over here. I'll just put that there. And so I'm going to copy down equation number 3. And so that's H2 plus half an O2. And then we say that goes to H2O. Okay. And we didn't do anything to it, so we're going to leave it as minus 285.8 kilojoules, and this we left alone. All right, we didn't do anything to it. All I did was copy it down. So I got to H2. Let me make sure I copied it down correctly. H2, half an O2 goes to H2O. Equation number 2, we just multiply times 2, so that'd be 2, 2, and 2. Okay, all right, and we didn't do anything to that. So I'm going to go ahead and put a check mark by 3. since we use that, and I'm going to put a check mark by the H2 up top since I used that. All right, moving left to right, I see I have C2H2, ethylene gas, and the only place where I see ethylene gas at this point is right here. Sure enough. Now, the ethylene gas is on the wrong side, and so that would be, I'd have to flip it over. I'd have to flip it to get the C2H2 on the right-hand side in my goal. And since I flip it, I'll also have to change the sign. And so we're going to take equation 1. Let me change colors here. Let's go with red on this one. Equation 1. I'm going to have to flip it, but I don't want to do anything other than that. I'm just going to flip it. I don't have to multiply times anything. So we're going to say equation 1, which is the 2 CO2s plus the waters. There's the water. Okay, and then it goes to the C2H2. That gets the C2H2 on the right-hand side, plus the 5/2 O2. And then we're going to just reverse the sign. We're going to just reverse the sign on equation number 1, which means it would be what? A plus 1299.5 kilojoules, and all I did was reverse. So equation number 1 we did times 2, equation number 3 we left it alone, and equation number 1 we reversed it. All right, and now I've used up all 3 equations. And let's see if we recover our original equation, because that's our check. If we recover the original equation, then we know we're good. So I look over here and I see 2 carbons. I don't see 2 carbons anywhere else, so we know that comes down. I see the 2 oxygens over here. And hopefully I'll see oxygens on the right-hand side as well. I see 2. And that's 5/2 right there. 2/2. 2 is 4/2. 4 is 4 over 4. No, 4 over 2, sorry. That'd be 4/2 plus a half makes 5/2. And so here's our 5/2 over here. So between the 2 of them, it does cancel. So there went my oxygens. Okay. And I look on the right-hand side on my first equation, and I see 2 CO2s, and I see 2 CO2s down here, and so that takes care of that. I see hydrogen. Now dropping down the equation number 3 here, I see the hydrogens. I don't see hydrogens anywhere else, so they survive and make their way down to the bottom. Okay, and then I see the waters, and where do we see waters? I see a water here, I see a water there, so the waters are gone, and the only thing that's left over now is the C2H2, and we are good as far as our goal equation goes. Okay, so we're able to get our goal equation from manipulating the original equations, and now we can safely go over here and say delta H is, and we say minus 787 minus 285.8, and then we say plus 1299.5. And I get positive 226.7 kilojoules. And there it is. Now, if you do not do this check over here, you may or may not get it right. You can still add the numbers together, they just won't be right. So our check is this part right over here on the left-hand side that I put in the black box. Is purely a accuracy or a correctness check. In other words, did I do the manipulation correctly? If I can recover the goal equation, then I know that when I add up the delta H's that it will be okay. And sure enough, I recovered the original equation, and that means the goal equation must be right. And so the delta H's, short of not putting it in the calculator right, should be okay, and they are. All right. And we can do this for 4 equations. We can do this for 5 equations. We can do this for 6. It just takes ever so much longer for each one to do them in turn. All right, questions on that? There are examples in the textbook. There are not very many in the textbook. You should work them all. You should go online just like I did, and this is where I got my example problems. I just went online and found them. Now, I used the problems online because these are not the easiest problems to create. Most problems I make up on the fly. These you just can't make up on the fly. So go online after you finish working the ones in the problems in the textbook, go online and find additional problems, okay? You will probably find this one as well. And they have solutions like reverse, change sign, multiply times 7/2, whatever you have to do. Okay, so they are online. Okay. All right. Now, good, clean fun doing Hess's laws. Like I said, it's like Sudoku for a chemist is what it is. All right. Now, in reality, like so many things we do in chemistry, after I show you how to do something like this, no one ever does his Hess laws calculations like that. The only time you'll ever see Hess's law calculations like what we just did is on a quiz, on a homework, on a test. This is, or in lab, that's coming up, is the only time you'll see where you're taking individual reactions, manipulating them, putting them together to try to get delta H of the reaction. In reality, that's too cumbersome because you would have to have millions of reactions and try to decide which set of reactions you're going to use to get your desired reaction. Much too much work. And so what we really do is we have something called enthalpies of formation. This is what we have that we actually use. Enthalpies of formation, and that is what's called from the elements. From the elements, okay? And so what we're going to say is that we're going to say delta H of formation of elements by definition is 0. We're going to say by definition of formation of the elements that you see on the periodic table by definition are 0. And so this makes the math a whole lot easier. If everything is set to 0, then 0 minus 0, 0 plus 0, 0 times 0 is still 0 all the way around. This is why we go through this trouble. And so, and we're going to add also this, we're going to say the diatomics, delta H of formation of diatomics is also 0. Diatomics being like N2, O2, H2, F2, ... Okay, those are your diatomics. Okay, N2, O2, H2, F2, Br2, Cl2, I2, diatomics. We're going to say those are 0. We're going to say the elements are also 0 as well. And so if you do that, you end up with this huge table on page, I think it's page 1200 in the back of your textbook, 1200. Let me see if I can find it real quick. It's either 1100 or 1200. I believe it's actually 1200. And we look, and here it is. Yep. And we look back on page, actually it's 1100. We look on page 1100 and we see this huge tables of what are called thermodynamic quantities for selected substances. And we see delta H of formation for a boatload of different elements on page 1100 near the back of your textbook. Okay, now having done that, what does that mean? It means that you can have a Hess's law equation that looks like this. You can say, well, what's the formation of H2O? And we'll say H2O gas because the state's actually important. And we would ordinarily, we would say, well, that we know how to do that. That would be 2, and that would be O2 plus 2 H2s gives me H2O, right? And there's my balanced equation for this guy. But what we would say from the elements, since we're only interested in just one, we would say from the elements, we would actually say 1/2 O2 plus H2 gives me H2O. And we're going to say delta H equals 0 for that. Delta H equals 0 for that. And then we look in our table on page, let's see, for water, that would be hydrogen, oxygen, H2O on page 1101. Let me fix that one right here. We look on page 1101 and we see delta H of formation for H2O gas. H2O is minus 241.82. And I got that off page 1101, and it's a table. And that's the energy of formation from the elements, assuming that delta H of the elements is 0. If you do that, then delta H formation for water is minus 241.82 kilojoules. All right. And we can do this for all sorts. There are tables and tables and tables, and there are very thick and very heavy and big books that are filled with nothing but these sorts of things. So you can take any arbitrary substance. And matter of fact, I put this part here, over here on the left, I put this part just for reference, and this is left off. And all we care about is this thing right there. That's all we care about. The fact that it's from the elements is now, from here on out, it's understood that when we talk about that delta H as a formation, it came from the elements, oxygen, hydrogen gas. They're considered the elements, diatomics. Or it came from, carbon, elemental carbon, or whatever. If it was like CH4, it's understood. The part that's boxed in with the green, it's understood that's there. But we now, from here on out, bless y'all hearts, from here on out, we don't care. All right, so let's take a look at an equation. Let's take a look at the combustion of methane. Now, we have this, and I want to know what's delta H of the reaction of this. Okay, this is what we're trying to find. These are the things that, as chemists, we're presented with a reaction, and we want to know how much energy are we either going to get, in other words, exothermic, negative sign, or how much energy is it going to take? And the way we're going to do this is we don't use Hess's law and manipulate equations and flippy flop stuff around and change signs and all that. What we do is we go find a table. We just go look it up. And so we could look up this reaction and find it, but let's say we didn't know what delta H reaction is. And the way we're going to do this is we're going to say the sum of the products delta H minus the sum of the products minus reactants delta H's equals delta H of the reaction. That's what we're going to say. We're going to say the products minus the reactants. Instead of, trying to decide, do we multiply times 2? Do we divide by 3? Do we change the sign? Do we reverse the direction? Do we do this, do that? We're just going to go to a table. That's what we're going to do. This is so much easier. Trust me. This is why we do this. Okay, so I go to my table, and I have my table in front of me on page 1100, and I need that in front of me. And I just make a list. So let's just start with, let's just make a list. CH4, we'll have O2, we'll have CO2, and we'll have H2O. And I'm just making a list, and it's all going to be, and when you have a homework or a quiz or a test or a problem or whatever, these things are generally given to you. But I have to look them up. So I'm going to say CH4, we're going to find carbon, and CH4 gas is minus 74.8. And this is kilojoules per mole, by the way. That's the units. Oxygen, what's delta H of formation for oxygen gas? If you look on the table, you will find an answer. But you know what? You don't even have to look on the table. It is by definition 0, because O2 is the natural form of the oxygen gas. So it is 0. And we look in under carbon again on page 1100, and I find carbon. I look for CO2, carbon dioxide, and it's not there, so it must be under oxygen then. And so I look for oxygen on page 1102. It'll help if I know my alphabet. There it is, 1101. And let's see, carbon dioxide. Okay, second column on the right, page 1100. This has actually got 2 columns. And so we say carbon dioxide is minus 395, minus 393.5. kilojoules per mole. Okay, now we're going to say that's gas. That's gas. Now it's important because if you look under oxygen, which is on the right-hand side of page 1101 towards the bottom right, you will see that there's 2 forms for water. You got H2O gas and you got H2O liquid. H2O liquid is minus 285.83 and H2O gas is minus 241.83. And this reflects the amount of energy that it takes to vaporize the liquid. The difference between the liquid and the gas form is the liquid going to the gas, you take a little bit more energy, so it has to go somewhere, so it appears in the formation. So I've specified that it's H2O gas, and I say minus 241.82. Minus 241.82 kilojoules per mole. There it is. Okay, so like I said, now I've got all of them up there, and like I said, this is generally given to you on homeworks, quizzes, tests, and so forth. But generally, this is presented to you in a small table. But I had to go through on page 1100, 1101, and pull them out. I mean, that's what you do. There's a little bit of legwork involved, but there's no manipulation. So now what do? We're just a good products minus reactants. So what's our products? This is where it's important that we know our right hand. Remember I said way back when I said, you got to know your left hand from your right hand? Remember I said that? Well, this is the case where you better know your left hand from your right hand. And so the right-hand side is your products. So these are your products. And these are your reactants. And it's products minus reactants. So let's take a look at the products. What's the products? It's carbon dioxide and it's water. So now, when I do these, and here's a pro tip for you when doing these. Liberal use of parentheses. If you feel like you haven't used enough parentheses, add some more. And this is because you're going to have signs. You got minuses and pluses are going to be going everywhere. And if you get a minus or a plus out of place with your calculator, it'll mess up your answer. Okay, so I find that the more parentheses I use, the less mistakes I make as far as getting it into my calculator. So what I'm going to do is I'm going to do reactants. So I'm going to say parentheses for my reactants. And I say, you know what? I have CO2 and I have one of those. Sorry, I'm doing products minus, yes, it's products minus reactants. I see 1 CO2 for my products. And so there's 1 CO2 down here. So I say minus 393.5. Now I'm going to leave off the kilojoules. I'm just going to leave it off because it's all understood to be kilojoules. So I'm just putting the numbers down. So it's 393.5. That's for the CO2. And there should be a 2 up here. So let's make sure this is a balanced equation. And so sure enough, there's a 2 there. And so there's 2 waters. So I'm going to have to say plus 2 times the waters, minus 241.82. See how I'm using parentheses everywhere? You could have said, well, I know what 2 minus a minus is, and that would be minus 4 something or another. All right, but I'm just going to use lots and lots of parentheses. So that takes care of the water on the right-hand side. Where did that 2 come from? That came from the balanced equation. It's important that it's balanced. There it is right there, okay? And so that would take care of my products. All right, and just so that I can have an intermediate number, usually I don't do intermediate numbers too often, but I'm just going to go ahead and do the minus 393.5, and then I'm going to say minus 2 times 241.82, and I get minus 877.14. All right, now that's for my products. Now for reactants, we're going to subtract off the reactants because it's products minus reactants. So we'll say minus parentheses. All right, what's my reactants? Well, my reactants is the 1-methane. So the 1-methane would be minus 74. See what I mean about the minus signs? That's a minus of a minus. So you know it's going to be positive, but your calculator takes care of these things. So a minus of a minus 74.8. And then we have the 2 waters, I mean, not 2 waters, the 2 oxygens. And so we're going to say plus 2 times, well, what's the enthalpy of formation for the oxygen? Well, it is 0. So 2 times 0, well, that's very exciting. 2 times 0 is 0, right? But I put it in there just to show you that it is there. And so we say, well, you know what? That was exciting. A minus times a minus gives me plus 74.8, and we're done. So products minus reactants, right? Products minus reactants. We did the products. That was minus 877.14 kilojoules. We did the reactants. Well, that was plus 74. And now what I do is just add them up. And so we say 74.8, and then we will minus 877.14, and I get minus 802.34. kilojoules. And that's delta H of the reaction for the whole thing. Delta H of reaction for the combustion of methane calculated from delta H of formations is about 802 kilojoules. And there it is. Okay, now I went through this step by step, so it took me a little while, but let me assure you that if you were doing this in practice, it's a lot easier to look up the numbers in a table than it is to try to find a bunch of equations, try to figure out which ones we're going to flip around, which ones we multiply, which ones we divide, whatever. This is a lot easier. It's much cleaner. So there you go. We have products minus reactants, and we get minus 80234. Now I wonder what the enthalpy of combustion of methane is. Let me take a look at this. So let's look that up. So we say enthalpy of combustion, CH4. And it says minus 890, wait a minute, let's see, heat of combustion, enthalpy of combustion, let's see it. And is minus 882. Minus 882, if I look it up on Google, right? Minus 882, what did we get? Minus 802. Hey, it's in the ballpark. It's in the ballpark. And this brings up a point which is your number that you're going to get. We're going to have several different ways of getting our delta H reaction, several different ways. And the numbers are going to be different from each other. They're going to be different a little bit. And depending on what you're trying to accomplish, whether you're building a bridge or just trying to determine, the enthalpy for, burning a Bunsen burner, it depends on which table you're going to go to and how much you're going to trust your answers, okay? And so the answers are going to be close, but they might not necessarily be as close as you would like them to be, but they'll be there. They'll be close enough. All right, close enough. All right, so I'm going to go ahead and stop recording here. Stop recording. There it goes.